In a distant galaxy, billions of light years away, a star 100 times the size of our Sun is dying. For a brief moment, it will unleash more energy than 1 trillion suns combined, causing shockwaves across spacetime. Tonight, we'll voyage through cosmic forces so powerful that they bend reality to their will. We'll see explosions that can outshine entire galaxies, black holes that consume light itself, and fundamental forces that hold the fabric of existence together. Prepare for a journey into power beyond your imagination. We begin. Deep within each particle of your body, an invisible conflict is raging. Protons packed together in the nucleus should rip apart immediately. Their positive charges reject each other with considerable force, similar to attempting to push two powerful magnets together, yet somehow, the universe's most powerful force keeps them frozen in place. The strong nuclear force operates at distances less than 1 proton, but its power is absolute. Scientists estimate that it is 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. Consider this: if gravity were a whisper, the strong force would be a thunderclap capable of shattering mountains. This force is transmitted through particles known as gluons, which act as invisible chains that bind, combines to produce protons and neutrons. The more you attempt to separate these particles, the stronger the force increases. It's like stretching a rubber band, which becomes thicker and more resistant. With every inch, you pull this strange conduct. The term confinement refers to the fact that no matter how much energy is applied inside each proton, it is impossible to isolate a single quark. 3 quarks dance inside a prison of pure energy. The gluons that hold them together carry the strong power itself, creating a complex web of interconnections. Even powerful supercomputers struggle to model them. When you try to separate quarks, the energy you give merely makes new quarks and gluons, similar to how cutting a chain causes it to sprout new links. The strong force works on such small scales that femcentimeters appears enormous. That's 1/4,000,000th of a meter smaller than anything you can fathom. At these distances, the familiar world of common physics collapses completely, and space and time become indeterminate, fluctuating in accordance with quantum mechanics' odd principles. This force forms the fundamental building blocks of matter. It specifies which atomic nuclei can exist and which cannot. It determines the rate at which stars burn nuclear fuel. It maintains the balance of creation and destruction in the hearts of all stars across the cosmic vacuum. Without the strong force, protons would rapidly separate due to electromagnetic repulsion. Atomic nuclei could not form fusion reactions in star cores, which would never begin. The universe would consist just of hydrogen atoms and unbound electrons. However, despite its immense power, the strong force has a terrible flaw. Its reach is limited to the border of an atomic nucleus. Beyond the microscopic level, it is about 1/100 trillionth the breadth of a human hair. Other powers gain control. Step into the larger universe, where distance is everything, and see what happens when gravity and light combine in the most intense explosions yet detected someplace in the cosmos. A beam of pure energy tears through space at nearly the speed of light in just 10 seconds. It generates more power than our Sun will produce in its entire 10 billion year existence. This is a gamma-ray burst, and it signifies the most powerful explosion that the cosmos can produce. These cosmic titans form when the most massive stars in the universe collapse into black holes. We're talking about stellar giants with a mass of 20 to 100 suns, burning through nuclear fuel at a rate that would deplete our Sun's entire energy supply in just a few million years. When these monsters have exhausted their fusion processes, gravity wins the ultimate war. As the star's core implodes, it discharges jets of matter and energy out its poles at 99% the speed of light. The collapsing core generates a newborn black hole surrounded by a superheated disk. The collapse caused magnetic fields to twist and become magnified, act like cosmic cannons. These jets are launched outward with unbelievable precision. The jets pierce the dying star like bullets through tissue paper, emerging as focused beams of destruction that collide tightly across enormous distances. Consider a laser beam that keeps its focus while traveling from Earth to the nearest star. These jets achieve similar results on a much larger scale. A gamma-ray explosion can outshine 1 trillion stars. If you could see gamma rays with your eyes, these explosions would be brighter than the full moon. Even from galaxies billions of light years away, the energy produced in seconds is greater than that of 10 trillion hydrogen bombs exploding per second. The most intense gamma ray burst detected in the entire history of the universe. In October 2022, the boat was nicknamed the brightest of all time. It was so powerful that it saturated gamma ray detectors throughout the solar system and caused noticeable changes in Earth's upper atmosphere from a distance of 2 billion light years. Imagine standing on Earth and seeing a flashlight beam from Alpha Centauri look as bright as a car headlight. That gives you an idea of how enormously powerful these events genuinely are. The light we see has traveled for billions of years, bearing news of stellar deaths from when the universe was young, when stars were more massive and ferocious than what we see now. Scientists have observed such remote explosions. Their light began to travel when the first stars were born, fewer than 1 billion years after the Big Bang. These ancient beacons provide glimpses into the early cosmos, when enormous stars lived quickly and died fiercely. Seeding space with heavy metals is necessary for future generations of stars and planets. But when it comes to what lies in the darkness between galaxies, even these giants pale in comparison. At the heart of our galaxies is a monster 4 million times the size of the Sun. Sagittarius, a star devours anything that comes too close, from gas clouds to whole star systems. However, this behemoth is regarded as insignificant in comparison to the actual giants of the cosmic deep. Some supermassive black holes have the mass of 40 billion suns packed into a space smaller than our solar system. They're like cosmic vacuum cleaners, with gravity so strong that nothing, including light, can escape once it reaches their event horizon. Space and time bend around them, like water spinning down a drain, resulting in distortions that would appear impossible if not seen directly. These gravitational monsters grew quickly. The most distant quasars appear when the universe was less than 1 billion years old, propelled by black holes that expanded to billions of solar masses in the cosmic equivalent of a few minutes. How could they attain such inconceivable growth? One of astronomy's most enduring mysteries. Normal stellar evolution cannot explain their existence. According to current understanding, these giants arose as huge seeds from collapsing gas clouds in the early cosmos. Unlike stellar mass black holes, which develop from dead stars, these primordial monsters could have had hundreds of thousands of solar masses from the time they were born. This head start enabled them to expand quickly by eating surrounding materials, also merging with other black holes. When gas spirals into a supermassive black hole, friction raises the temperature to millions of degrees. The material forms an accretion disk that shines brighter than 100 billion stars. The disk rotates so quickly that matter near its inner edge travels at large fractions of light speed. The most bright quasars driven by feeding black holes can be visible from all throughout the observable universe, with time dilation effects stretching seconds into hours for outside viewers. Like cosmic lighthouses, advertising their presence across billions of light years, they outshine their whole host galaxy, making the combined light of hundreds of billions of stars appear feeble in contrast. The most powerful black holes unleashed jets of particles at nearly light speed, creating beams that span hundreds of thousands of light years. These jets contain enough energy to remodel entire galaxies, scorching gas clouds to millions of degrees and preventing new stars from developing across enormous expanses of space. The jets can be operational for millions of years, continuously transferring energy into their surroundings. Recent investigations have uncovered black holes that appear to be too large for their host galaxies, challenging the conventional link between core black hole mass and galaxy features. These colossal giants test our understanding of how galaxies and their center black holes evolve together, but even these titans are subject to forces that act on scales beyond our conception. Every second, an invisible force wins a cosmic war spanning 13.8 billion light-years. It pulls galaxies apart, stretching the fundamental fabric of spacetime. This enigmatic power known as dark energy accounts for 70% of everything that exists. However, we know very little about what it is. Dark energy is unlike other forces. Unlike gravity and electromagnetism, it does not weaken with distance. Instead, when space expands, more dark energy appears to fill the gap. The larger the universe, the faster it expands. It's like a cosmic gas pedal that only knows how to accelerate, gaining strength as it pulls everything apart. In the 1990s, scientists accidentally found this force when researching distant supernova. They expected the universe's expansion to slow down due to the gravitational attraction of all its substance. Instead, they discovered that the opposite space is expanding quicker today than it was billions of years ago, as if by an invisible hand, pulling everything apart with increasing force. Imagine the universe as a balloon being inflated by an invisible breath. Dark energy is the breath that causes each point on the balloon's surface to travel away from the others. Galaxies travel across this expanding space like boats on a swelling ocean, unable to defy the tide that propels them into the cosmic deep. The universe's dark energy rises as space expands. This appears to violate conservation of energy, one of physics' most fundamental rules, yet studies constantly indicate that the energy density of dark energy remains constant as the volume of space expands. Where this extra energy originates from is absolutely unknown. Current hypotheses propose that dark energy could be a property of space itself. Einstein postulated a cosmic constant, which he later described as his worst folly. Others believe it could be a dynamic field that changes over time, or evidence that our theory of gravity on a cosmic scale requires considerable revision. Dark energy has far-reaching and catastrophic effects in the future. It will shred whatever we see initially. Galaxy clusters will fragment beyond recognition, forming solitary islands in an ocean of growing darkness. Individual galaxies will eventually lose their ability to withstand cosmic expansion. Even Autos itself may eventually be pushed apart in what scientists refer to as the Big Tear, and the stars will be extinguished. Planets will drift away from their suns, and even the fundamental particles that comprise matter will be separated by great distances. Dark energy, which appears peaceful today, will become the universe's ultimate destroyer, after destroying everything that gravity and the other forces have spent billions of years to create. Imagine compressing a mountain to the size of a sugar cube. The end outcome would still be 1,000 times less dense than a neutron star. These cosmic lighthouses contain the mass of our sun in a sphere about 12 miles across, creating gravitational forces so powerful that they twist light itself and bend space-time into inconceivable shapes. However, gravity is not their most scary attribute. Neutron stars have magnetic fields trillions of times greater than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, producing beams of radiation that sweep across space like cosmic searchlights, propelled by the universe's fundamental forces. A neutron star's magnetic field is extremely intense. It could delete every credit card on the planet from a distance of 600 miles. If you could reach within 1,000 kilometers, the magnetic force would be strong enough to remove iron from your blood. The field lines become visible as they trap and direct charged particle streams into narrow beams. When these magnetized neutron stars spin, they become pulsars, emitting radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, quicker than a kitchen blender, while maintaining impeccable timing that rivals the most precise clock ever created. Each pulse represents each rotation of a celestial corpse spinning in the darkness. The surface of a neutron star is a world of inconceivable physics, where ordinary stuff cannot exist. The magnetic field is so powerful that it causes atoms to expand into needle-like forms that align with the field lines. A typical atomic structure degrades completely, being replaced with strange forms of matter found nowhere else in the cosmos. Any ordinary mass that falls into a neutron star's surface is quickly compacted into a millimeter-thick coating. The gravity is so strong that a marshmallow dropped from such height would strike the surface with the power of a hydrogen bomb, unleashing more energy than all of the bombs used in WW2. Magnetar neutron stars have magnetic fields 1,000 times stronger, which is still close to the maximum strength permitted by physical rules. When these objects encounter magnetic quakes, their crusts break and move, releasing more energy in 1/10 of a second than the sun does in 100,000 years. These magnetic cataclysms produce massive flares that may be spotted from all throughout the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from 50,000 light-years away, illustrating the stellar remnant's extraordinary reach. The magnetic field surrounding a magnetar is so strong that it influences the vacuum of space itself. This causes it to become FRT, like a crystal. As light waves pass through this magnetized void, they become polarized, providing astronomers with first-hand proof of field strengths far greater than those obtainable in terrestrial laboratory. However, these stellar remains are simply the start of nature's most extreme creations. Invisible threads stretch over the observable universe, capable of cutting through planets like wire through cheese. These cosmic superstrings, if they exist, are one-dimensional particles that are thinner than a proton but potentially longer than galaxy clusters. They are wounds left over from the creation of the cosmos, marking phase transitions in the underlying structure of spacetime. According to string theory, cosmic strings generated within the first fraction of a second of the Big Bang. When the universe's fundamental properties changed rapidly, they acted like fissures in a frozen pond, indicating the boundaries where different regions of space crystallized slightly differently. As the universe cooled from its initial condition of perfect symmetry, a cosmic string only 1 meter long weighed as much as the Earth. Nonetheless, these objects are so thin that they are basically one-dimensional, with length but no breadth or height in the normal sense. They reside at the extreme edge of existence and nothingness, where matter, energy, reality, and pure mathematics are manifest. The energy contained within a cosmic string is nearly unimaginable. A string stretching from Earth to the Moon would hold enough mass energy to sustain human civilization for trillions of years. However, all of this huge energy is concentrated in a single line. Thin enough to have no observable thickness, cosmic strings are the ultimate representation of energy density when they flow through space. They cause ripples in spacetime, resulting in gravitational waves that can be detected by the most sensitive sensors. These waves would have a distinct signature that differed from those produced by black hole mergers or neutron star collisions, allowing scientists to potentially establish the existence of these hypothetical objects. When two cosmic strings overlap, they can form oscillating loops that look like guitar strings played by the universe itself. However, instead of producing sound waves, these vibrating loops cause distortions in the fabric of reality. These cosmic string loops progressively lose energy due to gravitational wave radiation, which sends gravitational waves rippling outward at light speeds. They gradually shrink, finally disappearing. A loop the size of our solar system would lose all of its energy in just a few million years, disappearing in a final flash of space-time distortion. Some physicists believe that cosmic strings could serve as cosmic highways, allows for faster-than-light transit across folded space. If two places in space were connected by a cosmic string, you could hypothetically travel down it and arrive at your destination faster than light. Traveling across regular space, cosmic threads would be the universe's ultimate shortcuts. Others believe cosmic strings could be portals into extra dimensions hidden from our three-dimensional universe. The threads could be fundamental objects that exist in higher dimensions, but only have one-dimensional cross-sections visible. In our world, these theoretical creatures are concealed in the mathematics of physics, waiting to be revealed or disproven by future observations 4 billion light-years away. A black hole the size of our solar system is releasing a beam of particles that spans the galaxy. This jet of plasma is extremely hot, moves at 99.9% of the speed of light, carrying enough energy to power 1 trillion stars while retaining perfect focus at distances beyond human comprehension. Quasar jets emerge from the maelstrom around supermassive black holes, where space-time itself becomes a fight between gravity and magnetism. As matter spirals inward toward its fate, it forms an accretion disk that spins at extraordinary speeds. The rotation of the disk causes magnetic fields to be magnified, twisting them into configurations that store large amounts of energy. These magnetic field lines function as cosmic particle accelerators, directing material from the inner parts of the accretion disk into narrow beams that emerge from the black hole poles. The same gravitational forces that should drive everything to destruction, instead, use this magnetic catapult device to propel material back into space at relativistic speeds. The jets are so straight they appear to have been drawn with a cosmic ruler, wielded by divine hands. They maintain their narrow focus over lengths of hundreds of thousands of light-years, weaving through space with accuracy. No human technology could compare. The collation is so flawless that jets seen with radio telescopes appear like narrow lines even from billions of light-years away. The particles in these jets carry energy that are millions of times larger than what we can generate in our most powerful particle accelerators on Earth. Individual protons rush along the jet at speeds so close to light that their relativistic mass increases by thousands of times, transforming ordinary matter into cosmic bullets of enormous strength. When a quasar jet points directly at Earth, it looks as a blazar, with the light brightening and fading as it sweeps by like a lighthouse. Within days or hours, these blazars' brightness can change by hundreds of times. Turbulence in the jet causes brilliant knots of emission that appear to be going faster than light. The geometry of observation creates an illusion of faster-than-light velocity. When stuff moving at 99% of the speed of light approaches us almost directly, it appears to span tremendous distances in absurdly short periods of time. The effect reveals how near these cosmic jets come to reaching their maximum speed. The most powerful quasar jets have enough energy to heat entire galaxy clusters and create bubbles in the surrounding plasma. That continues for hundreds of millions of years. These cosmic blowtorches can prevent new stars from forming over millions of light-years, effectively sterilizing enormous areas of space. Recent investigations have discovered jets that extend well beyond their home galaxies and into the intergalactic medium, where they continue to spread for millions of years. Black hole activity during the cosmic epoch, when the universe was younger and more violent than now. A white dwarf star in a binary star system, 30 million light-years away, is slowly taking material from its companion, much like a cosmic vampire feeding on stellar blood over millions of years. Hydrogen gas moves from the massive star to the compact remnant, piling up layer by layer like snow on a mountainside. However, This star snowball is approaching a dangerous threshold that will result in one of the universe's most precise explosions. White dwarf stars are the dense cores that remain after sun-like stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants compress the mass of our sun into a spherical. The vastness of the Earth produces materials so thick that a teaspoon weighs as much as a car. Their surfaces burn at temperatures of tens of thousands of degrees, which are hot enough to evaporate any known substance. The stolen material accumulates on the white dwarf's surface, where gravity compresses it into a thin shell of hydrogen, steadily increasing pressure and temperature. The white dwarf serves as a cosmic pressure cooker. Heat this stolen substance gradually until nuclear fusion begins to smolder in the surface layers. When the white dwarf approaches 1.4 times the mass of our sun, something awful occurs. This critical mass, known as the Chandrasekhar limit, is the highest weight that electron degeneracy pressure can sustain. Beyond this point, the star cannot withstand its own gravity. The stockpiled material erupts in a runaway thermonuclear explosion, destroying the entire star in seconds. The explosion spreads across the white dwarf like a flame front through cosmic dynamite, transforming carbon and oxygen nuclei to iron and nickel by explosive nuclear fusion. The star physically burns out of existence. This is a type Io supernova, and it depicts one of the universe's most accurate violent events. Every form of ES supernova produces about the same amount of energy, since they all involve the same mass of material undergoing the same nuclear reaction. This cosmic standardization makes them ideal for measuring distances over billions of light years. The explosion emits the light of 5 billion suns, visible from galaxies billions of light years away. For weeks, a single exploding white dwarf can outshine a galaxy with hundreds of billions of regular stars. The brilliance immediately peaks and then declines over months as radioactive materials generated during the explosion decay and release energy. The explosion creates, synthesizes, and disperses materials required for life across huge expanses of space. The calcium in your bones, iron in your blood, and nickel in coins were all created in the hearts of exploding white dwarf stars. These cosmic crematoriums scattered stellar ashes billions of years ago, and you are actually composed of them. The shockwave from a type Ia supernova travels at thousands of miles per second, scorching the surrounding gas to millions of degrees. The explosion may cause additional waves of star formation in neighboring gas clouds, while also enriching them with heavy elements necessary for planetary formation. Two city-sized objects swirl through space, trapped in a gravitational death dance that has lasted millions of years. They are neutron stars, or crushed cores of huge stars, and their collision will result in the most catastrophic catastrophe in the nearby cosmos. While forming elements more valuable than anything in a king's treasury, each neutron star has more mass than our sun squeezed into a sphere. Their surfaces are only 12 miles wide and made of atomic nuclei squeezed together so closely that a single teaspoon would weigh 6. There are billions of tons on Earth. These are not ordinary objects, but the most dense forms of matter that can exist without collapsing into black holes. The neutron stars alter each other's shapes as they orbit closer and closer together. Tidal forces stretch and crush these tremendously dense objects using only gravity. Like cosmic taffy, they generate heat, which causes their surfaces to shine at temperatures of millions of degrees. The orbital dance quickens as energy seeps away via gravitational waves. These gravitational waves deplete orbital energy at an ever-increasing rate, leading neutron stars to spiral inward faster and faster. Waves are ripples in space and time that stretch and compress the very fabric of reality as they travel forth at light speed. These waves can be measured by advanced detectors on Earth, even though they change distances by less than 1/10,000th the width of a proton. In the final seconds before colliding, The neutron stars complete hundreds of orbits per second, swirling around one another, faster than a helicopter blade. The gravitational waves that they produce become such. They extract the energy equal to 3 sun masses in the final few seconds before impact, causing the death spiral to increase rapidly. When the neutron stars collide, they produce a transient burst of gamma rays, followed by a longer-lived explosion known as an annova. The collision is really violent. It physically shakes the universe, sending gravitational wave signals detectable from billions of light-years away by sensitive sensors built to measure the impossible. The merging creates elements heavier than iron, using a process known as fast neutron capture. Atomic nuclei are hit with so many neutrons during the collision that they can only absorb a fraction of them. This produces unstable neutron-rich isotopes, which decay into stable heavy elements like gold, platinum, and uranium. A single neutron star merger creates enough gold to weigh multiple Earth masses, as well as comparable amounts of other precious metals. The impact ejects this celestial treasure at velocities nearing 1/3 the speed of light, filling neighboring space with materials that will eventually make their way in future generations of planets and asteroids. The impact ejects material in several components that move at various speeds. The fastest moving debris causes the first gamma ray burst, while slower material forms expanding shells that glow with radioactive decay for weeks. This chi-nova light is then produced by billions of freshly formed atomic nuclei, undergoing radioactive decay, resulting in a fire. The 4 fundamental forces that govern everything in the modern universe were unified into a single, unimaginably powerful interaction that held sway over reality itself in the first fraction of a second less than the time it takes light to cross a proton. And the universe expanded faster than light itself. This phase of cosmic inflation expanded space by billions of billions in less time than it takes to blink. Space did not explode into pre-existing emptiness, but rather generated new space as it expanded, bringing matter and energy along for the voyage. During these early moments, the temperature was so intense that even the fundamental forces of nature struggled to keep their individual identities. Gravity, electromagnetism, and strong and weak nuclear forces were all indistinguishable manifestations of a single superforce that has never been since the first instance of creation. As the universe expanded and cooled, this cosmic unity broke like glass that cooled too quickly. The forces split through a sequence of phase transitions, which released massive amounts of energy and established the fundamental structure of physical law. Gravity separated first, followed by the strong force, and eventually electromagnetism broke from the weak force. The cosmos cooled enough during the first minute, following the Big Bang, to allow the formation of the first atomic nuclei, protons and neutrons, through a process known as Big Bang nucleosynthesis. Newly born cooling quarks came together in a cosmic forge, producing the majority of the hydrogen and helium we see today. The energy density was so high that matter and antimatter annihilated each other in continual bursts of pure energy. For 300,000 0000000 remained opaque to light because unbound electrons dispersed photons so efficiently that light could only travel a short distance before being absorbed and remitted. The cosmos was like a bright fog, full of energy yet impossible to see. During the cosmic dawn, electrons and atomic nuclei eventually merged to form the first neutral atoms, allowing light to flow freely for the first time. This cosmic clearing produced the afterglow known as cosmic microwave background radiation, a faint echo of creation that spans the entire sky. The Big Bang was not an explosion in space, but rather an explosion within space. It created both time and matter, establishing physical principles that govern everything from quantum fluctuations. No event prior to or since galaxy formation has equaled its ability to create everything from nothing and provide the groundwork for existence. However, even this cosmic birth may not be the ultimate limit of strength in our universe. Beyond the regular supernova is something significantly more violent. When a star 50 times the mass of our Sun exhausts its nuclear fuel, it does not simply collapse and explode. It causes a hypernova, which is a very energetic explosion. It outperforms typical supernova by a factor of 10 to 100, emitting the energy equivalent of billions of atomic bombs detonating every second for millions of years. These stellar monsters are extremely rare. Even on cosmic timescales, only the most massive stars in the cosmos can cause hypernova, and they must be spinning fast when they die. The combination of tremendous mass and rotation results in extremely violent situations. That regular stellar death cannot contain the wrath that is about to be unleashed. When the core of such a star collapses, it nearly immediately becomes a black hole, but the star's rapid rotation prohibits a simple symmetric collapse. Instead, the falling material forms an accretion disk around the nascent black hole, which spins so quickly that it becomes a cosmic dynamo, producing magnetic fields of incredible strength. These twisted magnetic field lines behave similarly to springs that have been stretched to their limits. When they ultimately snap and reattach, they send 99.9% of the matter and energy forth. At the speed of light, these jets bore into the falling star like cosmic drill bits, carrying enough energy to power our Sun for billions of years. The jets ripped through the star's outer layers and exploded into space, creating gamma-ray bursts we can detect from billions of light years away. But the carnage doesn't stop there. The shock wave from the jet's passage heats the star's interior to temperatures higher than those found in normal stars' cores, triggering explosive nuclear burning throughout the stellar remnant layer after layer of the star explodes outward in a cascade of thermonuclear violence, converting carbon to neon. Silicon burns to iron in seconds. The energy released by these rapid fusion events fuels the destruction, resulting in an explosion visible from the edge of the observable cosmos. A single hypernova can produce more heavy elements than dozens of regular supernova. The intense conditions produce radioactive isotopes that decay over weeks and months, providing power in the aftermath. Low levels persist long after the initial explosion. Many of the elements required for life are produced by these cosmic forges and dispersed throughout large expanses of space. The most powerful hypernovas can impede star formation across whole galaxies. Their shockwaves compress adjacent gas clouds, causing further waves of stellar birth, while also heating the surrounding medium to temperatures that preclude additional star formation. Two huge galaxy clusters race toward each other at thousands of miles per second across hundreds of millions of light years. Each cluster comprises thousands of galaxies, trillions of stars, and immense oceans of superheated gas that emit X-ray photons. When these cosmic giants meet, they produce the most energetic events in the universe since the Big Bang. Galaxy clusters are the cosmos' greatest gravitationally bound structures. When clusters of this size crash, the resulting mass is equivalent to 100 trillion suns. The energy emitted is millions of times greater than the total output of all stars in both clusters. The collision occurs slowly by cosmic standards, with the clusters approaching each other over hundreds of millions of years. Dark matter, which accounts for the majority of each cluster's mass, is solely impacted by gravity and survives the collision relatively unscathed. However, the hot gas that fills the space between galaxies has a totally different fate. As the clusters merge, their gas clouds collide with each other. At speeds nearing 5,000 miles per second, the impact generates shock waves that heat the gas to temperatures above 100 million degrees, hot enough to remove electrons from any atom. The resulting plasma emits bright X-rays, resulting in some of the most luminous things in the cosmos. These cosmic collisions can result in the development of radio halos that span millions of light years. The collision stretches and amplifies magnetic fields, accelerating electrons to near light speeds and forcing them to generate radio waves as they spiral around field lines. The end product is a ghostly radio glow. The most severe cluster collisions, which are larger than entire galaxies, can cause bow shock. That spreads outward at thousands of kilometers every second. These cosmic sonic booms compress and heat the surrounding medium, resulting in formations visible from great distances. The energy contained in these shocks exceeds the combined energy output of billions of supernovae during the collision. Individual galaxies in the clusters have their own violent interactions. Tidal forces can remove stars from the galaxy. Skirts produce extended streamers of star debris, tracing the cluster's gravitational dance. Certain galaxies may be entirely disrupted, their stars dispersed throughout the developing cluster's halo. The collision could result in huge bursts of star creation. As gas clouds within galaxies are crushed by the encounter, these starbursts can enhance a galaxy's star formation rate by hundreds of times, resulting in dazzling blue regions loaded with newly formed massive stars that will live quickly and die young. A possibility exists deep inside the quantum foam that underpins all reality, so terrible that it might wipe out everything we know in an instant. The Higgs field, which gives all particles their mass, may not be in the lowest possible energy state. If this field suddenly dropped to its true minimum, it would generate a bubble of destruction that would grow at the speed of light, rewriting the laws of physics and annihilating everything it encountered. The Higgs field permeates every area of space, including the vacuum between atoms, like a ball balanced on a hill. This field may currently be in what physicists refer to as a fake vacuum state. It appears stable, but it could potentially fall to far lower energy levels, profoundly altering the nature of reality itself. If vacuum decay started any place in the cosmos, it would result in an expanding sphere of genuine vacuum, moving outward at the same speed as light. Nothing could escape this cosmic wave of annihilation, since neither information nor matter can travel faster than light. We would have no warning of its approach until it entered the bubble of real vacuum. The fundamental tenet of nature would be that various particles might have varying masses. Alternatively, it might not exist at all. Atoms, as we know them, cannot form. The strong nuclear force might weaken, forcing all atomic nuclei to break apart instantly, rendering chemistry and biology impossible. The energy difference between the false and actual vacuums would be released as the bubble grew. This energy may exceed the rest mass energy of all matter in the universe, making vacuum decay more powerful than transforming every proton, neutron, and electron into pure energy. Would flood the cosmos with more power than all of the stars in the galaxy put together. Current simulations indicate that our vacuum may be metastable, balanced perilously on the brink of stability. High-energy events, such as cosmic ray collisions or black hole evaporation, could potentially cause the transition. Even quantum fluctuations may spontaneously form a bubble of real vacuum in empty space. The fact that vacuum degradation is unavoidable is alarming. If the false vacuum state exists, quantum mechanics ensures that every metastable state will decay, even if the probability is extremely low. Over the immense durations of cosmic history, even the most implausible events become certain. Vacuum decay would be the ultimate cosmic reset button. Everything that has ever existed, including every star and planet, and living things, would be eliminated, replaced by a cosmos with radically different physics. Our current reality would vanish, leaving just the remembrance of its existence. According to certain hypotheses, vacuum decay may have occurred several times over the course of the universe, with each shift resulting in new regions with different physical laws. We may be living in only one bubble among many, surrounded by realms whose rules of existence are completely alien. In the early moments after the Big Bang, when the cosmos was smaller than an atom and denser than the center of a neutron star, tiny fluctuations in density could have collapsed to generate black holes larger than mountains, but smaller than atoms. These primordial black holes would have gravitational fields so powerful that they would twist space and time on scales beyond human perception. Unlike black holes created by collapsing stars, primordial black holes can have any mass. Some may weigh as little as a paperclip, while others may be more massive than our Sun itself. The smallest would be quantum things, in which the odd rules of quantum mechanics clash with the absolute authority of general relativity in ways we don't fully grasp. A primordial black hole with the mass of a mountain would be tiny than a proton, but have a gravitational field millions of times stronger than anything we could build on Earth. Space and time around such objects would be twisted into inconceivable shapes, creating realms where the traditional conceptions of distance and length have no significance. These minuscule monsters would be among the most violent objects in the cosmos. According to Stephen Hawking's estimates, black holes release radiation and gradually dissipate over time. The smaller the black hole, the faster and more violently it dies. A primordial black hole with the mass of a big asteroid would erupt with the force of millions of hydrogen bombs. The closing moments of a little primordial black hole's life would be stunning beyond belief as it shrinks to subatomic scales. The rate of evaporation increases dramatically in its final second of life. It would emit more energy than our Sun does in a single year. Everything is concentrated in a spot smaller than an atomic nucleus. If primordial black holes exist in vast numbers, they could address one of cosmology's most perplexing mysteries, the nature of dark matter. These invisible objects would exert gravitational impact without emitting light, precisely matching the features observed in dark matter throughout the cosmos. The search for primordial black holes has led LED scientists to investigate some of the most severe regions in the universe. When these objects pass by stars, they heat the stellar material, causing noticeable brightness variations. When they collide with neutron stars, they may produce detectable gravitational wave signals. Some primordial black holes may have expanded throughout cosmic time by accreting stuff, also merging with other black holes. These things may currently be lurking in the dark gaps between stars, invisible predators ready to strike matter. They can consume the gravitational lensing effects. Light from distant stars may occasionally be bent and magnified. The largest primeval black holes could have been the seeds of the supermassive black holes that we witness now at the centers of galaxies. This would answer the question of how such massive black holes could have formed so early in the universe's history, when regular stellar evolution had only begun. Before the cosmos was barely 1 second old, space saw the most furious expansion in cosmic history in less time than it takes for light to cross a proton. The universe expanded from less than an atom to larger than a grapefruit. Cosmic inflation is the most powerful force ever unleashed, extending space faster than light, and laying the foundation for all that happened during inflation. Space expanded by at least 10 to the 26th power in just 10 to the negative 35 seconds. To put this into perspective, consider a single atom suddenly growing larger than our solar system in less time than it takes light to travel its width. This expansion was so quick that it is beyond human comprehension. The primary force for inflation was a quantum field known as the inflaton, which filled all of space with immense energy density. Unlike ordinary matter, this field had the unusual virtue of generating additional energy as space expanded, operating as a cosmic fuel that never ran out. The more the universe expanded, the more energy became available to fuel future expansion. Inflation resolved some key issues that had perplexed cosmologists for decades. Before inflation, the universe would have been full with strange particles and topological flaws that should still be seen now. The fast expansion of these things caused them to grow to sizes greater than the observable universe, thereby burying them beyond our cosmic horizon. The expansion occurs during and was so extreme that portions of space that were once in contact were stretched far beyond the point of communication. This explains why the cosmic microwave background radiation has nearly identical temperatures in all directions, despite the fact that these regions could never have exchanged energy. As the expansion began, quantum fluctuations in the infill field during inflation were stretched to cosmic scales, resulting in density variations that would later grow into galaxies and galaxy clusters. These tiny ripples in the fabric of spacetime became the seeds of the universe's large-scale structures. From the smallest stars to the most massive superclusters, the quantity of energy involved in cosmic inflation was simply amazing. In just a fraction of a second, the infill field released more energy than all of the stars in the cosmos. Over the last 13.8 billion years, this energy has been used to create new space, and filling it with the materials and radiation that we see now. When inflation ended, the inflaton field dissolved into ordinary matter and radiation, warming the universe to temperatures greater than 10 to 28 degrees. This was hot enough to generate and destroy particles at speeds that would make the cores of the most massive stars appear ice-cold in contrast. Some hypotheses propose that inflation did not occur once. However, it is an eternal process that constantly creates new regions of space-time outside our observable world. In this scenario, our entire universe could be just one bubble in an endless multiverse in which new universes are constantly created through inflation at the center of a dying star, revolving at 1,000 revolutions per second. Magnetic fields 1 trillion times stronger than Earth's are about to cause unimaginable damage. This is a magnetorotational supernova, where the combination of tremendous spinning and magnetic strength produces explosions that dwarf even the most powerful gamma-ray bursts. Created magnetic fields so powerful that they could tear apart atomic nuclei hundreds of kilometers away as the universe's most massive stars died. Some have magnetic fields similar to those observed on Magnetar. If such a star is also quickly rotating, when its core collapses, the conservation of angular momentum accelerates the collapse, much like a figure skater pulls in their arms during a pirouette, as the stellar core shrinks from the size of Earth to only 12 miles. Its rotation rate increases millions of times. The magnetic field lines frozen in the falling plasma are twisted and amplified until they achieve maximum strength. That approaches the theoretical limits set by physics. These fields become so powerful that they can alter the structure of space and time itself. The magnetic pressure in these strong fields exceeds that of atomic nuclei. Field lines are stretched to the breaking point. Store enough energy to power the sun for billions of years. When these magnetic structures become unstable and rejoin, they unleash the stored energy in tremendous magnetic explosions that make solar flares appear like calm breezes. The combination of rapid rotation and intense magnetic fields produces a cosmic dynamo that is more powerful than anything else in the cosmos. Charged particles trapped in these fields are accelerated to energies that far beyond those achievable in our most sophisticated particle accelerators. Individual protons gain enough energy to break atomic nuclei via pure kinetic impact. These magnet-rotating explosions can propel jets of magnetized plasma at speeds near light. Unlike the jets seen in typical gamma-ray bursts, these magnetically powered outflows maintain their focus beyond cosmic distances, producing destructive beams capable of sterilizing planets millions of light-years away. The magnetic fields produced by these explosions are so intense that they alter the vacuum of space itself. At field strengths greater than 10 to the 15th Gs, the quantum vacuum becomes biot, dividing light into separate polarizations and producing optical effects found nowhere else in the cosmos. Space itself transforms into a kind of cosmic crystal. With directed qualities, matter exposed to extremely strong magnetic fields exhibits behaviors that appear impossible. Atoms are stretched into needle-like forms aligned with the field. The chemical bonds that keep molecules together are twisted and deformed beyond recognition, and even the fundamental particles that comprise atoms begin to behave in odd new ways. A mega rotational supernova can emit hundreds of times more energy than a regular supernova. The explosion creates exotic isotopes that cannot be produced under any other conditions, resulting in elements that survive for only a few seconds before disintegrating into more stable forms. In the huge halos around each galaxy, these cosmic alchemical laboratories produce elements that test the limits of nuclear physics. An invisible material weighs 5 times more than all of the stars combined. This dark matter experiences gravity but interacts with nothing else. We grasp the concept of a shadow cosmos which shapes cosmic structure while remaining completely concealed from our eyes. However, if dark matter particles ever collide with their antimatter counterparts, they could cause explosions that resemble supernova. If they were their own antiparticles, they would annihilate when they collided, transforming their entire mass into pure energy. According to Einstein's famous equation, annihilating 1 kilogram of dark matter produces the same amount of energy as 21 million tons of explosives, making it the most efficient energy source. Theoretically possible at the dense cores of galaxy clusters, when dark matter concentrations are highest, these annihilation events could result in a cascade of high-energy particles and gamma rays. The energy emitted would be greater than the total output of all the stars in the cluster, creating radiation that might be detected from billions of light-years away. Some ideas propose that dark matter particles could be substantially more massive than regular protons and neutrons, with the energy equivalent of hundreds or thousands of hydrogen atoms compacted into a single particle. When such enormous particles collide, they produce particle showers of immense energy, which trigger cascade events that produce unusual particles found nowhere else in nature. The annihilation process may produce pairs of photons with energy millions of times larger than visible light. These gamma rays would contain the signature of dark matter disintegration, giving us a direct look into the properties of this unknown element. The most energetic annihilation events may create photons with energy reaching the Planck scale, where quantum gravity effects become crucial if dark matter annihilation happens preferentially in high-density locations. It may produce feedback effects that shape the distribution of matter on cosmic scales. The energy released might heat neighboring gas, preventing it from collapsing and creating new stars. The radiation emitted by dark matter annihilation has the potential to sterilize entire galactic regions. In their center regions, in the harsh environment, near black holes, where dark matter densities can reach remarkable levels, annihilation rates may rise to the point where they contribute significantly to overall energy output. These events may provide visible signatures in the form of high-energy neutrinos, or gamma-ray flares, which may indicate the presence of dark matter concentrations. According to some theoretical models, dark matter annihilation could cause chain reactions in which the energy released creates conditions conducive to further annihilation events. However, these cascade annihilations have the potential to deplete large regions of space of dark matter, leaving cosmic voids filled with high-energy radiation. The search for dark matter annihilation signals has led scientists to investigate the universe's most extreme settings. Galaxy centers with high dark matter density are ideal for discovering the telltale gamma-ray signs of annihilation. The lack of clear signals thus far suggests that either dark matter does not self-annihilate, or the process occurs considerably less frequently than previously thought. Protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles speed through the galaxy at 99.99999999999%. The speed of light compresses individual energy equivalent to a baseball thrown at 60 mph into a single atomic nucleus. The cosmic accelerators that generate these particles operate at scales and efficiencies that make even the most advanced technology appear primitive. The highest energy cosmic rays detected on Earth carry energies that exceed 10 to the 20th electron volt, which is more than 10 million times the energy attainable in the Large Hadron Collider. A single one of these particles holds enough energy to light a small bulb for a limited period of time, all contained in a smaller object than a proton. When such particles enter the Earth's atmosphere, they cause cascades of secondary particles, which can trigger detectors spread across thousands of square miles. Cosmic accelerators. One of the most perplexing puzzles in astrophysics is what causes these powerful particles. While supernova shockwaves can propel particles to high energy, they cannot account for the most intense cosmic rays. The electric fields required to accelerate particles to such energies would have to span over millions of light years and maintain voltages greater than 10 to 20 volts. Active galactic nuclei driven by big stars. Black holes are the most plausible cosmic accelerators. Magnetic fields near these objects can store vast quantities of energy, which is then released in short bursts that accelerate particles to relativistic speeds. The jets emitted by these black holes serve as natural particle accelerators. Millions of light years long, far beyond any human-built machine, cosmic ray particles pass across magnetic fields in space. They are deflected and scattered, making it nearly hard to trace them back to their sources. Only the most energetic particles remain. Those with energies greater than 10 to the 19th electron volts move in relatively straight lines through galactic magnetic fields. These ultra-high energy particles are our only first-hand observations of the universe's most severe acceleration processes. Some of the most stunning occurrences in astrophysics result from the interaction of cosmic rays and magnetic fields. When these particles spiral around field lines, they produce synchrotron radiation, which glows across the electromagnetic spectrum. The radio emission from our galaxy is mostly caused by cosmic ray electrons swirling through the Milky Way's magnetic field. Cosmic ray acceleration can occur through a variety of mechanisms, each working on a different scale and creating particles with a distinct energy spectrum. Shockwave acceleration happens when particles repeatedly collide. Fronts gather energy with every crossing. Magnetic reconnection can cause particles to accelerate impulsively when twisted field lines snap and reorganize themselves. The most intense cosmic ray events may utilize completely distinct acceleration processes that we have yet to uncover. Some theories propose that the disintegration of unusual particles left over from the Big Bang could produce cosmic rays with energy greater than those achievable by conventional acceleration. These hypothetical particles may be remnants of physics outside the standard model. Cosmic ray interactions with gas and dust in space produce secondary particles such as gamma rays, neutrinos, and positrons. These secondary products contain information regarding both cosmic rays and